Let's consider a mass on a spring. So this picture shows a mass that is attached to a spring on a horizontal surface, but this is really no different than a vertical surface, or hanging from something vertically. So just remember that as we move through this. So when we consider a mass on a spring, it's just like saying, well, a bungee jumper, when he jumps, he's increasing in speed because of the vertical acceleration of gravity, and until the elastic cord attached to his ankles start to stretch. And then the kinetic energy of his motion is then transformed into the elastic potential energy of the cords. So down, down, down he goes, and then once the cords reach their maximum stretch, his velocity reverses. So he raises up in the air as the elastic potential energy of the cords is transferred back into kinetic energy. So he jumps, he's all kinetic energy until the cords start to stretch, and then they're gaining elastic potential energy. He reaches the bottom, his velocity reverses, and then that elastic potential energy gets transformed back into kinetic energy and he goes up. So if he keeps on bouncing, that's called simple harmonic motion. And this happens again and again and again until friction takes over and he stops. So in this example, at this first point, the object begins at rest. So someone or something is holding it at this furthest location, and its potential energy is maximum. And then as the spring contracts, the object speeds up until it reaches the center point. So it's speeding up through right here. And then it has maximum KE, or kinetic energy, at this middle location until the spring starts to compress. So as the spring starts to compress right here, the spring is gaining back some of that elastic potential energy to have just potential energy at the end of its motion at this point here. So we're purely potential at the beginning, purely potential at the end, and now that it's compressed, if we were to keep drawing this diagram, it would move back to this location. Keep moving back and back and back and back, and friction would take over, and the distance that it moves back each time would lessen over time. So when we're talking about springs, we have an equation to determine what is the potential energy of that spring. Well, the potential energy of that spring, or sometimes people call it U, is equal to 1/2 kx squared, where k is the spring constant, and x is the distance from the equilibrium point. So in this case, you have to be careful about where is this equilibrium point. Where in this case, it's this line here. So our 1/2 kx squared would be the distance from this line. So here we have the greatest potential energy, and here we have the greatest potential energy in a non-friction setting, which is just not real. But in a pretend world where we don't have any friction, we could talk about the entire energy of the system always remaining constant. And so if our block is moving, so anywhere that it's moving in between these 2 points, sorry, that makes it look a little odd, in between these 2 points. Anywhere that it's moving, it has kinetic energy, which you guys have heard about before. Kinetic energy, the energy of motion. So our kinetic energy is still the same, or our equation is still the same, and that's 1/2 mv squared. And the m in this case is the m of this particular block. So the total energy in this particular system, since we don't have any gravitational potential energy, is just the total energy is equal to K plus U. So that's equal to 1/2 mv squared plus 1/2 kx squared. So you can see this graph down below that shows both of the kinds of energy. The red line on top is this total energy, the blue line is potential, and the green line is kinetic. So our potential is highest on the ends, decreases as it goes through that equilibrium point, and our kinetic energy is the exact opposite, 0 at the ends, and it increases until it reaches its maximum at the equilibrium point and then decreases again. When we talk about the maximum displacement, so the maximum x, a lot of times we call that location A. Sorry, that should say max. So at the furthest point here, so anywhere here or anywhere here, our equation, because there's no kinetic energy, would just be E is equal to 1/2 kx squared, but because we're at our max distance, that would become 1/2 ka squared. So just at those two maximum points would we use this. Otherwise, always use 1/2 kx squared, and if for some reason that confuses you, just keep it at 1/2 kx squared, and just know when you're talking about a maximum x versus another x location in any problems. So we could do a practice problem with all of this. Sorry, it takes me a while to erase all this. Okay, so if we have a mass of 1.5 kilograms and it slides across a horizontal frictionless surface, so for these kind of problems you just have to pretend, at a speed of 2 meters per second until it collides with and sticks to the free end of a spring with a spring constant, so that's, remember, K, of 50 newtons per meter. We haven't learned much about newtons yet, but remember, newtons are a mass times acceleration, so that means it's a kilogram meter per second squared. So make sure you keep those units correct. Remember, that's a kilogram meter per second squared. And the problem said the spring's other end is anchored to a wall. What it wants to know is how far has the spring compressed when the mass is, at least for an instant, at rest. So that means how far does it compress before it gets pushed back the other way. Because of the law of conservation of energy, we can say that the total energy of the mass before it hits the spring will be equal to the total energy in the, or the total potential energy of the spring when it's compressed, because that kinetic energy will go away and there's no potential energy when the mass is moving before it has hit the spring. So the Ke before spring is equal to 1/2 mv squared, and we know that the potential energy of the spring when it's fully compressed is going to be 1/2 kx squared. So this winds up being fairly simple because we know the total energy in the system doesn't change. So if that's true, then 1/2 mv squared needs to equal 1/2 kx squared. So all we need to do now is rearrange and solve. So we can simplify both sides. We have a 1/2 on both sides, so that just cancels out. So we have mv squared equals kx squared. And what we're looking for, remember, is that compression distance. So we're solving for this x. So mv squared over k, the square root of that will give us x. So if that's the case, then, or x, yeah, the square root of that will give us x. So we wind up getting x is 0.35 meters. And that tells us that the spring compressed 35 centimeters. So that's a pretty big distance. That's probably because it's a pretty large mass and it's going fairly quickly. 2 meters per second is not chump speed, and 1.5 kilograms is quite large. So that in our heads should make sense, 35 centimeters for the compression of the spring.